Okay, now that we've gotten used to vectors a little bit more, and we've talked about a couple of operations, we now need to talk about two of the big operations as they relate to multiplication. So there's not one way to multiply two vectors together. There's two different types of multiplication. Now, you might say, well, we've already talked about multiplication. No, we've talked about multiplication between a constant multiple and a vector. I'm talking multiplication between a vector and a vector. And so there are two main ways to do this. One's called the dot product and the other's called the cross product. And they are very different, but they are also ways of multiplying vectors. So we have two ways of doing multiplication when it comes to vectors. So dot product is first. Dot product is definitely the easier of the two. And dot product is probably the closest to what you might think multiplication of vectors could be. But there are some things we need to discuss here. So first, let's look at a dot product. And so definition of dot product here is if we have two vectors, let's say vector v and vector w, they're in the same space, they're both in Rn, that's important. You have to have the same number of components for each vector. And if you don't, we can talk about taking a vector and bumping it up to the higher dimensional space like we have in the past, but we cannot bump it down. And so then the dot product between these two vectors, v and w, is going to be a constant for now, because what we're talking about is vectors that have components that are all constants. What I'll say more generally is that the dot product between two vectors will be equal to whatever the components are made up of. So if the components of a vector are made up of constants, then the dot product between two vectors will be a constant. However, if the components of two vectors are made up of functions, let's say, which will happen eventually, then the dot product between two vectors will be a function. Okay? What it is not is another vector. Okay? That is not what you would get when you get the dot product between two vectors. So the sum of two vectors is another vector. The difference of two vectors is another vector. The dot product between two vectors is not another vector. Okay, so that's something to be aware of. All right, so if we do v dot w, and the notation is very important. You do multiplication, we have all sorts of notations when it comes to numbers, right? So if I do 2 times 3, I can use the dot. I do 2 times 3, I can use the x. I do 2 times 3, I could just put a parenthesis around one of them or even around both of them. All different ways to denote notation, but they're all the same, right? They're all 6, okay? That's not the case with vectors. With vectors, the notation makes a huge difference because the type of multiplication is different. So dot product, we use the dot. Pretty simple. What we do is we multiply components. So v1 times w1, the first two components. We multiply the second two components, v2 times w2. The third components, the fourth, up to the nth components. Remember, they're in the same space, Rn, so they have the same number of components. And then we add all those things together, okay? And that's what the dot product will give you. So remember, the dot product is not another vector. It's a constant in this case, okay? Or it's whatever the vectors are made up of. Sometimes you'll also hear this as the inner product, okay? So let's look at a couple of vectors and let's look at a couple of dot products here. So let's look at v to be a two-dimensional vector and w to be a two-dimensional vector. Here's z. The z is a five-dimensional vector. It's got 5 components. And b, there's another 5-dimensional vector. So let's look at a couple of dot products. Let's do v dot w. So if we were to do v dot w, very simple. We take the first two components and multiply those together, so that would give me -2. The two second components, multiply those together, they give me -15. Then add those, so then I'm going to get -17. So that's the dot product of v and w. If I was to do w dot v, notice we would actually get the same thing, because now we're just taking the first components of w and v, but they're the exact same. It's -2, and w and v for the second components, which is -15, and we still get -17. So when you switch the order around, what do we get? We get something that we call commutative. Addition, subtraction, dot product, these are all commutative operations. The order does not matter, okay? V dot w, w dot v. v plus w, w plus v. It's all the same, okay? So that's that. What if we did z dot b, okay? Well, here's z and b, so we do the first two components, so then we would get 2. The second two components, we would get positive 3. The next two components, we would get negative 10, and then negative 21. And then finally, 9 times 6, we would get 54. Okay? And add those all up. This is a 10. And what do we get? We get 5 minus 10 would give me negative 5. And negative 21 gives me negative 26. Negative 26 and 54 would give me, so 28. And there's your dot product. All right, but what if we wanted to do the dot product of, say, z and v? Well, there's a problem. The problem is that v has 2 components and z has 5 components. What I'm going to do is I'm going to rewrite v. And if I rewrite v as 1, negative 3, 0, 0, 0, that's still the same v. I just bumped that v up into this 5-dimensional vector by just putting zeros on all those new components there at the end. So now it's still the same vector. Again, we've talked about this. It's still the same vector, but now I can add it with z. And so what's going to happen, though, it's going to be very simple, is that when I do z dot v, I'm going to get 1 times 1, which is 1, negative 3 times negative 3, which is going to give me 9. Oops, I'm messing this all up. I said 1, and then 9. I should add them together. I was putting that in a vector form. That's not a vector. Remember, I just got done saying that. And then I do 0 times, 0 times, 0 times, which will just give me 0, 0, and 0 for those, and so I would just get 10. And so z dot v, since I'm putting zeros on all those last components basically just zero out. So I'm really just looking at the first two components. All right, finally, if I did v dot v, so a vector dot itself, I'm going to do 1 times 1, which is 1, negative 3 times negative 3, which is 9, add them together, I get 10, which just happens to be the same thing as z dot v. But notice what that is. What that is the same thing as the magnitude of v squared. Well, what's the magnitude of v? The magnitude of v is the square root of the first component squared plus the second component squared. Okay? So negative 3 squared. I guess I could write it like that. Right? And then the square root of it. But if I square that, what happens? This and this cancel, and I just get what's inside the square root. And that's exactly what I have here, 1 plus 9. And so any vector dot itself is the same thing as the magnitude of that vector squared. It's the magnitude basically without the square root. It's a thing inside the square root. Just keep that in mind. Okay. So we see the dot product is really not that hard to do computationally. Just a couple quick properties we've already looked at is that, one, it is definitely commutative, that the order in which you do it does not matter. v.w, w.v, they are the same. We call that the commutative property. You should know that. If we try to mix some operations here, so addition of vectors and dot product, so something more along distribution property, how does that work? Well, it works the same way distribution property would always work when you combine multiplication and addition. So you do v in here and v also in here, so v.w, then v.z, and then you would add those together. If I try and combine constant multiplication along with dot product, so basically two different types of multiplication, I can do the dot product first and then do the constant multiple, say lambda, which is a constant multiple. Or I can multiply that constant multiple n times v first and then do the dot product, or I could do the constant multiple times w, then do the dot product. If I do the dot product between the 0 vector and any vector, again, order doesn't matter. Whether I do it in first or second, I should get 0 because the 0 vector, every component is 0. And if I did the dot product of v in itself, we all said that already, it's the magnitude squared. So now we get into some of the geometric aspect of the dot product. And what can we use the dot product for? What does the dot product give us geometrically? Well, there's nothing directly that the dot product gives you geometrically. Like if I look at the answer I got for some of those dot products and the answer was 5 or -10 or 7, there's not a whole lot you can glean out of that single number, but the more we get used to this idea of how we use the dot product for a geometric purpose, you can use that number a little bit more. And so the way we use the dot product geometrically is to use it to find the angle between two vectors, which will start getting us more into the concept of how we find the direction of a vector. Direction is very much based off of someone's perspective, okay? And you can have a standard perspective. Think about our navigational perspective of north, south, east, west, that no matter which way you're facing, north is always going to be the same direction on your compass. Okay, it's always going to be pointing in the same direction. So whether I'm turning one way or another, north is always pointing towards the North Pole. So we can have a standard direction, which if we were thinking about, say, in 2 dimensions, standard direction would be a direction based off of a vector in standard position or an angle in standard position, which would be off the positive x-axis. So if we look at an angle off of the positive x-axis, that can help us figure out the direction of our vector. Okay, that would be the closest to a standard direction. But really, direction is relative. It's based off of your direction as it relates to something else. So if you were standing at one location and you were to turn into the north, that would tell you to rotate a certain direction around to another position. So where you were originally and then where you ended up, the angle between those could tell you the position that you are now looking. And so the angle between two vectors will help us figure out the direction of any vector based off of another. And the way we find the angle between two vectors, let's say v and w, is by a very simple formula, and it's this formula here, which is the cosine of theta, theta being the angle between the vectors, equals v dot w over the magnitude of v times the magnitude of w. I could rewrite this formula by saying theta equals the arc cosine of v dot w over the magnitude of v times the magnitude of w. I could write it that way, which would just solve for theta itself, and that would be the angle I'm looking for. But writing it this way looks a lot nicer than this arc cosine. But nonetheless, that's how you'll find theta. And so if I was to say, let's find the angle between two vectors, okay? So I have one vector, say, here. I have another vector, say, here, and I found the angle between them. It would give me the idea of the direction of each based off of the other. Because if I told you that the angle between two vectors is 90 degrees, you would automatically be able to draw a picture like this. Now, maybe you draw it like that, or maybe you draw it like that, but nonetheless, you know the relationship between two vectors in terms of each of their directions and the other. If I said the angle between two vectors is 45 degrees, you might draw something like that, right? And you would know it. And if I said based off of standard position, so if I got rid of all this, you would definitely know that if I said a vector's angle off standard position is, say, 60 degrees, you would automatically know where the direction of that vector is and what direction it is pointing in. Okay, this would be our 60-degree angle. So angle will definitely help us find this direction. All right. So if I gave you two vectors like, say, this, and I said, let's find the angle between them, and these are two 3-dimensional vectors. We could also do this with 2-dimensional vectors. We should use this formula. And so if I call this one, let's say v, I call this one, say, w, and I did, say, v dot w, because I'm going to need that. That would be very simple. 3 times 1 is 3. Negative 1 times negative 1 is 1. And 2 times negative 2 is negative 4. I add that all together. That's going to give me what? Negative 1 and 1 is 0. Okay. Then I do the magnitude of v, and I find that. I do the magnitude of w, and I find that. So that'll be the square root of 9 plus 1 plus 4. I just take each of these components and square them. And this will be the square root of 1 plus 1 plus 4. Again, square each one, add them together, take the square roots. So what do I get? I get the square root of 14. I get the square root of 6. Okay. And if I was to look at the formula, I'd have the cosine of theta. Oops, lost it. Cosine of theta equals the dot product over square root of 14 times the square root of 6. Well, 0 over anything, as long as it's not 0, is actually 0. So I have the cosine of 0. Cosine of theta, sorry, equals 0. So theta equals the arc cosine of 0. Which would give me what? Well, I got to think about this. Cosine of 0, cosine of theta equals 0. Or the arc cosine of 0 equals what? Well, I'm looking at what angle. What angle, when I take the cosine of it, do I get 0? And also remembering that when you do something like arc cosine, you're stuck within a certain range of values you can have, remembering all the way back to your inverse trig functions. But the answer here is pi halves. Okay? So pi halves is the answer. That's the angle. So that tells me that the two vectors that I'm talking about, v and w, meet at a 90-degree angle. Okay, the angle between them, if this is v and this is w, just randomly drawn, the angle between them is pi halves. And so that tells me a little bit about the relationship and the direction of each of them based off of the other. Now, let's look a little bit closer here. The dot product was 0, which no matter what the magnitudes were, we knew that this was going to give us, okay, 0. And so what this tells us is that the cosine of theta equals 0 is always going to give us pi halves. We look that backwards and we say basically, all right, well, if the dot product between any two vectors happens to be 0, we know that those two vectors meet at a 90-degree angle. And we can say that they're perpendicular, but more likely we're going to use the term orthogonal. So orthogonal means meets at a 90-degree angle, but we usually use the term orthogonal because we're talking about vectors. If two lines meet at a 90-degree angle, we would call them perpendicular. If two vectors meet at a 90-degree angle, we usually call them orthogonal. And then if we talk about a vector and a plane, which we'll get into eventually, so you have some plane here, you have a vector, and that vector meets the plane at a 90-degree angle, we call that normal. So we change the terminology, but they all mean 90 degrees, and we change it based off of what elements we're talking about. Lines, vectors, plane in a vector, or line in a vector, we also could say normal. But they all mean 90 degrees. But anyway, when I said that you can look at a dot product and not glean a whole lot out of that number, that's not completely true. The more you understand how that dot product works inside this larger angle formula, you can get something out of it. So if you ever see the dot product between two vectors being 0, you could know that essentially that the cosine of pi halves would equal 0, and the only way that this could equal 0 is if the numerator equals 0. So that means anytime the dot product equals 0, the angle between those two vectors had to have been pi halves, or 90 degrees. Another thing we use the dot product for is something called a vector projection. And so a lot of terminology goes in here, but more, I think the geometric concept is more important here. But nonetheless, let's look at the vector projection and discuss some terminology and some geometric qualities of this vector projection. And so let's say we look at two vectors, let's say u and v, okay? Let's say they're non-zero vectors, right? They're not the zero vectors, so they have magnitude, they have direction. And u is essentially the sum of two vectors, say w1 and w2, where w1 is parallel to v and w2 is orthogonal to v. So, we could say it's the sum of those two vectors. None of that necessarily matters a whole lot, but that just gives us some terminology here in that w1, which would be this vector that's here, that's parallel to v. We call that the projection of u onto v, or the vector component of u along v, and we denote it by this proj vu, where v is the vector we projected onto, and u is the vector we started with. So the projection of u onto v, that order is actually really important. The projection of u onto v is denoted this way, as opposed to if I did v onto u would be different. W2 would be u minus w1, so the subtraction. We know what subtraction geometrically looks like. That's called the vector component of U orthogonal to V. Again, this terminology not as important as the geometry of it. So let's look at this. So I have two vectors here. I have V and I have U. Okay? And I want to project U onto V. U onto V. So that's very important. So what I'm going to do is I'm going to extend V out infinitely. Okay, this way. Okay, with a line. And what I'm going to do is I'm going to drop a perpendicular down, okay, from the end of U to where it hits that line. Okay? And I'm going to come up with this point right here. Okay? Then what I'm going to do is I'm going to connect the vector from this initial point where U and V started. And I'm going to go all the way out to that point. Right? And I'm going to look at that new vector there. So we got that new vector. That new vector right there, that long red vector, that's the projection of U onto V. Okay? That's the projection, and I just used the wrong notation, the projection of U onto V. Okay? So that's based off of this being an acute angle also. So that's some of the things to worry about. If it wasn't an acute angle, let's say we have this picture here where we have, all right, here's V, okay, here's U. Now the angle is an obtuse angle. I'll do the same thing. I'm going to extend a line through V. I still want to go U onto V. But now when I drop a perpendicular from the end of U down to that line, it's now going to hit over here. So V went this way, remember, right? Okay. So the projection of U onto V is now starting from this initial point going this way. But still, that's my projection. And, you know, geometrically, I think that's pretty easy to do. You're just talking about right triangles here. But nonetheless, that's the projection of U onto V. Again, a lot of this vector component of U orthogonal to V business is not as important. W1 and W2 not as important, other than the fact that W1 is the projection vector. Okay, but how you get it geometrically is pretty simple. Computationally, if we were to do it, let's say we have two vectors V and W instead of V and U. It doesn't really matter what we call them. They're in the same space. It's important. And we wanted to do the projection of V onto W, okay? V onto W, so that's what this is talking about. This is V onto W, okay? The way we would go and do this is simply with this formula of V dot W over the magnitude of V squared times W itself. And notice that should kind of make sense in the geometry of it. Think about it. If we're projecting of U onto V, this vector here is just a scaled version of V. So it's a multiple of V. Well, look at this. This is a multiple of W. And we're projecting onto W. And so that's what a projection is. It's just a scaled version of the vector you're projecting onto. Order matters here. It's pretty important. So if I did the projection of W onto V, notationally it would look like this. Okay, this is W onto V. And the formula would be still V dot W because the order of that doesn't matter. But here's where it would be different. I do the magnitude of V squared times V itself. Okay? So I want to be a multiple of V in this case since I'm projecting onto V, and so that's where the order changes. So if I look at this here and say, okay, here's V, here's W, those are two vectors, and I'm using the bracket component here, notation instead of the triangle bracket, the square bracket, but remember they're the same thing. I try not to use that too much, but when typing it's actually kind of easier to use the square bracket sometimes, but nonetheless. Projection of V, in this case W onto V, and this one would be V onto W. So let's do each one. So the projection the projection, all right, of W onto V. I need the dot product of V and W, so that's going to be 12 plus -2 plus -5. So 12 plus -2 plus -5 over the magnitude, in this case, the magnitude of the one we're projecting onto. So we're projecting onto V, so I need the magnitude of V, so that would be, and I'm squaring it, so it's just the thing inside the square root, and so that would be what, 9 plus 4 plus 1, and then I'm going to multiply that by V itself, which is 3, -2, 1, and so what you see here is this is going to be, what, 5 over 14 times 3, -2, 1. And I can leave it like that. I mean, that's just a multiple times the vector, so you kind of see what's happening there. I can distribute this in, and I can write this as 15 over 14, and I can write this as -10 over 14, which I'd write as -5 over 7, and then this one can be 5 over 14. I can write it like that. But nonetheless, that's your projection vector, and it's just a scaled version of, in this case, V. And if I were to do it the other way for the other projection, the big difference here is that this would be the magnitude of W squared, and this would be W. So if I was to switch that out, I would definitely switch this around. So this would be now W, this would be V. This here would become the magnitude of W squared, so it would just be 16 plus 1 plus 25, and this right here would change to be 4, 1, -5. And so the computation would work out to be roughly the same. Take away all this, and you would get still 5 here for the dot product, but obviously this number is different and this vector is different. So you could figure that one out from there. All right, now the other operation we need to talk about is cross product. This is another type of multiplication. Far more complicated type of multiplication than dot product is. Computationally, dot product should be really easy to do. You should be able to do 10 dot products in the course of a minute's time, right? Easy. Cross product a little bit more involved when it comes to the computation, and geometrically more involved as well. And so let's look at the definition of a cross product. And so let V and W be some vectors in three-dimensional space. That's pretty important. Is that this cross product really is only going to make sense to us in three-dimensional space. You cannot do the cross product between two-dimensional vectors. So that's a big difference between dot product and cross product there. If we want to do the cross product between V and W, we would use the cross notation for multiplication, so that's very important. The notation is key here. And computationally, well, we're going to get another vector. Okay. If you don't like the bracket notation with the square brackets, I could put the triangle brackets here on the end. But nonetheless, we're going to get another vector out of this. We definitely get another vector. And the first component of the vector is made up of this right here. So you see it's V2W3 minus V3W2. And then the second component is V3W1 minus V1W3. And the third component is V1W2 minus V2W1. And that's based off of, V having the components V1, V2, V3, and vector W having the components W1, W2, W3. Okay? And so you see, pretty involved here. And I can tell you right now, you're not going to memorize that. Right? You can if you want, but I don't memorize it. It's a pattern. There's a pattern to this that you're going to want to come up with. But before we get into that, let's look at geometrically what we get. Here I'll use U and V instead of V and W, but it doesn't really matter. So if I look at two vectors, V and W, or V and U, okay, look at these two vectors. They could have any angle between them. It doesn't really matter what that angle is. It looks kind of like it's 90 degrees here, but it's not. Okay. I could always make a plane that those two vectors sit on. There's always a unique plane that two vectors make up. Okay, so these two vectors make this plane. What the cross product of u and v gives me is this vector right here, which is orthogonal to both u and v at the same time. So u cross v meets u and v both at a 90-degree angle simultaneously. So it's normal to this plane, we could say, or we could say it's orthogonal to both u and v simultaneously. So that's what the cross product gives you. So the cross product gives you another vector, and it gives you this orthogonal vector to both u and v. The direction could be slightly different because you can think of maybe this vector right here also meeting u and v at a 90-degree angle. So whether it's this one or this one, we'll talk about that a little bit. There's also something called the right-hand rule, which will help us determine what direction the cross product is pointing. But nonetheless, geometrically, that's what you get. So you get a vector that is orthogonal to both u and v at the same time, regardless of what the angle between u and v was to start. It doesn't matter what that angle is. That could be anything. This angle here between u cross v and u cross v and v, that has to be a 90-degree angle in both cases when you do the cross product. All right. Now let's look at this computationally. Okay. Yeah, this is the formula, and then, you can memorize that, but it's really a pattern of determinants. Okay. When it comes to this formula, and determinants are a computational element working with matrices. And so we got to go over a couple of things here. If you're in linear algebra or you have linear algebra, you know what I'm talking about already. If not, we can go over real quickly this concept of a determinant. And so a matrix is a rectangular array. So we talk about a square matrix, which is a square array of terms based off of rows and columns. So we can look at a matrix that's, say, A, B, C, D. It's a square array. We use the brackets to denote, okay, this is the matrix here. These are the components of that matrix. And this is called a 2x2 matrix in that it's got 2 rows and 2 columns. So let's call that matrix A. Okay? And then we want to find the determinant of that matrix. So one notation for the determinant of a matrix is to put the straight bar on either side. We could also write the determinant like this of A. Either way, the way we do it with a 2x2 matrix is to take this times this. So this first element in column 1, row 1. In this case, this is column 2, row 2. So AD minus, then we do these two, multiply together, so BC, and that would give us the determinant. It's a very simple way to find the determinant of a 2x2 matrix. Order matters, so again, column 1, row 1 times column 2, row 2, minus column 2, row 1 times column 1, row 2, and we do the subtraction between them. So that's the determinant of a 2x2 matrix. Okay. Now we look at a 3x3 matrix. Okay. And what I'm going to do is I'm going to look at it in this way. So let's get rid of a lot of this. Okay. And let's call this matrix I, J, K as the first row. Let's call V1, V2, V3 the second row. Let's call this W1, W2, W3 is the third row. And we're going to find the determinant of that 3x3 matrix, okay, where this is V and this is W. Okay, so I put the first vector in the second row, second vector in the third row, and the first row is IJK, which relates to the, the components of the standard basis vector notation that we've talked about already. All right, so the way we do this is very simple. So we look at the first one. We're going to do this by a series of 2x2s. So we look at the first one. We go I. I is the first component, right, of any vector. And so we look at I, and what we're going to do is we're going to look at that row and column. I'm going to cross those out. What I'm left with is this 2x2 matrix that sits right here. And I'm going to find the determinant of this 2x2 matrix. And that determinant will then be multiplied by I. And so that would give me V2 W3 minus V3 W2. And that would be my I, which means my first component, which just so happens to be exactly what you're looking at here as the first component of the cross product. Then I'm going to do that again with the second component, so that'll be my J. Again, if I cross out that row and that column, okay, here, I'm left with these four terms, these two and these two, which those four terms create another 2 by 2 matrix, okay? And what I can do here is do V1 times W3 minus V3 times W1. And so I get V1, what did I say, V1 times W3 minus V3 times W1. Now if I look at that, and I look at that comparative to what I see here, it's not the same. Order's wrong. My order's off. The subtraction needs to be reversed. What I have to do is I have to multiply that one by a negative to switch the subtraction off. But that's my J component. That's my second component. So it's multiplied by the J. And then I have one more, which we'll call our K component. So let's use purple here. It's my K component. So I cross out that row, cross out that column. Now I get this 2 by 2 sitting right here. And I'll do again this and this. Okay. I've run out of room here, so I'll put it here. So I got V1W2 minus V2W1. And again, that's exactly what you see up here. Okay. So I add that on, and that's my K component. And so those are my three components of my vectors, which is exactly what the cross product of V and W is. Okay? And so this, determinant of this 3 by 3 matrix I created is how I find the cross product. So if you look at that pattern of 2 by 2s, that's how you come up with this, this, and this. Just remember that the second one, the J component, the middle component, is the order's wrong from what it's supposed to be in the actual cross product. So what we do is to correct that, we multiply by a negative. And a lot of this could be explained when you get to linear algebra and you learn more about determinants and certain properties of determinant operation. But nonetheless, that one's going to be multiplied by a negative so that we could switch the order around. Some people say, well, let me just do the diagonal the opposite way. So if I have, say, V1, W1, and V3, W3, that's the 2 by 2 we're talking about here. Let's do this one first minus this one. Let's switch the order around already. I don't like doing that because I think students make more mistakes doing that. The traditional way is to just multiply that middle one by a negative to flip the subtraction around. Okay, so you have this pattern. Very simple. Okay, let's do some examples. Okay, so let's look at a couple of examples here. So three different cross products we're going to do. U cross V, V cross U, and V cross V for these two vectors, U and V. So let's look at U cross V first. So what I want to do is I want to create my determinant of my 3 by 3 matrix. So let's go I, J, K. Since it's U first in the cross product, the order is going to make a difference, and that's why we're going to do these two different orders here. So I'm going to put U in the second row, 1, negative 2, 1, and V in the third row, so 3, 1, negative 2. All right, so if we were to do this cross product, what are we going to do? We're going to do the I, so it's this 2 by 2. And so what I'm going to get here is 4 minus 1. Here's my I, that's this minus this, okay? Then I know I need a minus on this next one, and so this is my J, so I have this and this. So if I do that, I'm going to get negative 2 minus 3, that's my J, plus, now I do my last one. And so let's choose the green, so it's my K, so that's this 2 by 2, and so I'm going to get 1 minus negative 6, so 1 minus negative 6, and that's my K. So what I end up with here is 3I, this will give me negative 5 with this extra negative, so positive 5J, and this will be a double negative, so 1 plus 6 is 7, 7K. I could write this in component format. I don't need necessarily the IJK notation. This is the same thing as 3, 5, 7. Okay? But nonetheless, that's your cross product. A little more involved than dot product was. The more of these you do, the faster you get at it, and you can be able to get a bunch of these done in a short period of time when you have some practice at it. All right, so let's look at V cross U now. Okay, so V cross U, again, I'm going to set it up, I, J, K. Now it's V, so that would be 3, 1, negative 2, and U, which is 1, negative 2, 1. So which one is in this order here matters, right? This is the second row, this is the third row. And there's a reason for that, right? And the reason is you're going to see that when I do this, and I do my I, which is this 2 by 2, I'm going to get 1 minus 4. That's my I, minus, I do the next one. My J would be this and this. So that'll be 3 minus negative 2. That's my J. And then my K would be this 2 by 2 here. So that'll be, what, negative 6 minus 1. That'll be my K. And you see what we get here. We're going to get negative 3I. This will be plus 2, so 5, and the extra negative will be minus 5, J, and then this will give us a minus 7K. And comparing that to what we got before, what we really have here is negative 3, negative 5, negative 7. So we get the negative of the original, which if this was, say, U cross V, then this is V cross U. So they're pointing, when you get the negative, you get a vector that points in the opposite direction. All right? And so they're not the same vector, right? They are not the same vector. They're not pointing in the same direction. And so the order definitely matters. U cross V does not equal V cross U. So cross product is not a commutative operation. Okay? So that's pretty important to understand. But how you do it doesn't really necessarily change, in that it's this 3 by 3 determinant of this matrix that we create, where first row is IJK, second row is the first vector, third row is the second vector. All right? All right, let's do one more. Let's do the cross product of V and V. All right, so remember, V was this vector 3, 1, negative 2. Okay, and we're going to do the cross product of V and V. So if we do V cross V, all right, we're going to set that up. Still the I, the J, and the K. But V was 3, 1, negative 2. So we have that for the second and the third row. Okay? And if we were to do this, same idea. The I would be this 2 by 2. So this minus this. So we're going to get negative 2 minus negative 2. That's my I. Minus, the next one would be my J, so that's this one and this one, so that'll be negative 6 minus negative 6. That's my J, and then finally my K, which is these, so that would be 3 minus 3, and that would be my K, but notice what we get. This will give me 0, this will give me 0, this will give me 0. So when I do the cross product between these two vectors, I get the 0 vector. Well, that happens with these two vectors. What can we say about any two vectors, V cross V? Well, actually the same thing's going to happen. That when you do the cross product between any two vectors, you're going to end up with the 0 vector. And the reason why that is this. Remember, cross product between any two vectors, so let's say U and V, is this vector that's perpendicular to both of them, orthogonal to both of them. Well, if you do the cross product of V and itself, so let's get rid of U here. So it's V cross V, okay? There's not just one vector that's orthogonal to that. That one's orthogonal, that one's orthogonal, that one's orthogonal, that one's orthogonal, that one's orthogonal. Like, there's infinitely many different vectors that are orthogonal to this vector. And by doing the cross product with itself, you're trying to find the vector that's orthogonal to itself. And so that's why the 0 vector comes out. And so anytime you do the cross product between a vector and itself, you'll get the 0 vector, because essentially there's not a unique answer to the geometric interpretation of this. So just know that. So order matters. Do the cross product of vector and itself. You know what you get. These are all important things. So here we have what we call the right-hand rule, which helps you describe the direction in which the cross product is pointing. So we've talked about how the cross product is orthogonal to both the two vectors in the cross product. So let's say we're looking at the cross product of A and B. So A, we meet that at a 90-degree angle. B, we meet that at a 90-degree angle. So there's your cross product. Well, we can use what we call the right-hand rule. So obviously you need your right hand to do this. We use our forefinger to represent vector A. We use our middle finger to represent vector B. And there's some angle, say, between those two vectors. And you could describe it, with those two fingers. So if A is pointing this way and B is pointing this way, we would position our hand in that direction. Whatever direction your thumb is pointing, okay, will always be the direction of the cross product, right? Again, using your right hand. So if I reposition my hand, say, on an angle and say, okay, here's V, here's B, here's A, all right, there's the cross product. Okay? And if I flip this around and I do it upside down, and so that now this is B and this is A, and I'm looking at the cross product of B and A, again, same idea. So I position my hand however I want to. So if I looked at it, and I look at these two vectors here without my right hand, so I look at this and this. So here's A, here's B. Again, index finger, middle finger, thumb points this way, so there's this. Whereas if I flipped it, and now this is my index finger and this is my middle finger, I would have to rotate my thumb around. I'd have to rotate my hand around to make that happen, to put this here and to put this here. In which case my thumb would be pointing down, and that would be the cross product. So we'd be going, the cross product would flip around and give us the negative. And so you see how the right-hand rule would work with our fingers. This is often important when we're doing an application and understanding which direction these vectors are pointing. So a few properties of the cross product, again, some we've already talked about, is that the order does matter. So in terms of commutativity, it is not a commutative operation. So U cross V does not equal V cross U, but it equals the negative of V cross U. Okay. If we try to combine cross product with addition and think about the distributive property like we did with dot product, same idea. U would have to distribute into V and W. So U cross V plus U cross W. This should be a W here. Constant multiple times the cross product. You do the cross product first, then the constant multiple, or you can multiply the constant multiple into one of the two vectors before you do the cross product. But you don't multiply it into both. I think that's a mistake a lot of people make, is they'll multiply this cross product into both of these, but that's not the case. You multiply it into U, or you multiply it into V before you do the cross product. You don't multiply it into both. Any vector across the 0 vector will always give you 0 no matter which way you do it. Cross a vector with itself, you get 0. We saw that. And then we can mix the dot product and the cross product. This is called the triple scalar product, which we'll talk about in a minute in a little more detail. But it's a mix of the dot product and the cross product. And what this is telling me, when you look at this, is that if I do U dot V cross W or U cross V dot W in terms of which ones I cross and which ones I dot, doesn't really seem to matter. So here I'm crossing U and W, or V and W, and then doing the dot product with U. Here I'm doing the cross product of U and V, and then dotting that with W, and I'm getting the same thing. They're equal. The key is, though, in both cases, if you look at it, is that the cross product has to come first, and the dot product has to come second, because that would make sense. When you do the cross product, you get a vector, and so then we do this vector dot this vector. Whereas if you do dot product first, you would get a constant, and then you'd have to cross that with another vector. It doesn't make any sense. You can't do that. You don't get elements that work out. But which two you cross first and then which one you dot second doesn't really make a difference. And so we'll see that a little bit closer in a minute. So as far as geometric properties of the cross product go, the main one is what we've already seen, is that U cross V is orthogonal to both U and V at the same time at that right-hand rule. But another one is talking about areas of a parallelogram. We know that two vectors create a unique parallelogram, okay, to those two vectors. So we've seen that. We know what the diagonal of that parallelogram is. That's the sum of the vectors. We know that this diagonal would be, say, the difference of the vectors. But let's talk a little bit more about the area of this parallelogram. Well, what happens is that the magnitude of the cross product can be found by using this formula here, that the magnitude of U times the magnitude of V times the sine of theta. But what that magnitude actually equals is the area of the parallelogram. So the magnitude of U cross V actually gives you the area of the parallelogram. Now, there's a reason for this, okay? Thinking about how we would find the area of this parallelogram. So real quick little proof here. So area of the parallelogram needs two things. We need this distance here, the height of the parallelogram, and we need the length of the base, okay? So those are the two pieces we need. Well, the length of the base, if we call that U the base, that would be the magnitude of U, okay? So that would be the length of this base here. As far as this height here, we could create this right triangle, and it's essentially the side opposite of this angle theta. So theta is the angle between V and U. This side here is the opposite side to that. So if we look at that in terms of V, we could say that the sine of theta equals the opposite over the hypotenuse, in which case the opposite side, which would be this side for right now, well, let's just call it, say, X, it's what we don't know. The hypotenuse is going to be the magnitude of V. That's the hypotenuse there. So the distance, which would be the magnitude of V, would be that length. And so if I wanted to find what the opposite side is, I could take this and move this to the other side of the equation. And so that opposite side would give me that the opposite side would equal sine of theta times the magnitude of V. And so the height of this parallelogram is that. And then the way we find the area of a parallelogram is essentially by doing the length of the base times the length of the height. So this times this. So magnitude of U times the magnitude of V times the sine of theta would be the area. And that is exactly what the magnitude of U cross V would equal. And so we see that, all right, well, that's the area of the parallelogram. Also, what we have here is an alternate formula for finding the angle between two vectors, which, to be honest with you, you'll never use, but we could. If you look at this equation right here, and I solve for the sine of theta, you would have the magnitude of U cross V divided by the magnitude of U times the magnitude of V, in which case you could also solve for theta by doing the arc sine of both sides. But we never use this formula. Why? Because it's a lot harder than the cosine formula. Because we have a cross product, which are harder to find than dot products are as part of our formula. So we would never really use this, but you could say this is an alternate form of finding the angle between two vectors. A couple of things here. U cross V equals 0. If and only if U and V are scalar multiples of one another. We said that basically they're the same vector, just different magnitudes. Or U and V are parallel, which is the same thing as scalar multiples of each other. So they kind of go hand in hand with some of the geometric properties that go along with cross product, but this is the big one here. Okay, so we can find the area of this parallelogram using a cross product. And that's the main geometric property I want you to get out of this, aside from what the basic definition is. Now I want to talk about something called the triple scalar product that we discussed just a couple minutes ago, in which we're combining dot product and cross product. And so what we could do is you could do it one at a time, right? We can find the cross product. That would be another vector here. And then whatever we get out of that, we can dot that with U. But there's a way we can do this faster. And the way we do that faster is by doing a 3x3 determinant, similar to the cross product itself, but instead of just doing the cross product of V and W, which would be this, and calling this I, J, and K to start with, that would just give us the cross product of V and W. That would give us this. What we're going to do is we're going to replace that top row with U, and what that does is it actually does the dot product as we're doing the cross product, okay? And so it's easier to do it this way, well, I should say it's faster to do it this way than to do the cross product first with the IJK as your first row, and then do the dot product second. Remember, we always have to do the cross product first, no matter what, but nonetheless, this makes it a lot easier. But we also said a second ago that the order doesn't really matter here. So all that would change is if I said, let's do V dot U cross W, what would change is where I put those vectors in terms of the different rows. This would be V's row, this would be U's row, and this would be W's row. All right? And so that would be the only difference when I change out this dot product and cross product, the triple scalar product. Now, geometrically, what that gives you is it's going to give you what we call the volume of a parallelepiped that is created by U, V, and W. Parallelepiped is a nice way of saying a box. So if you have three vectors, say here's one vector, here's one vector, here's another vector, here's a third vector, and they're not all coplanar. Coplanar means they don't all fall in the same plane. Remember, any two vectors will create a plane, right? You can take any vectors and create a plane, but the third vector doesn't also fall in that plane. So what happens here is if we transpose all these vectors over and over and over again, what we get is this box. Sometimes it looks like a nice neat box, straight up and down. Sometimes it looks like a box that someone sat on, so it's kind of tilted. But nonetheless, this is what we call a parallelepiped. And if we wanted to find the volume of this parallelepiped, okay, the space inside of it, the triple scalar product will do that. So that's really the case. If the triple scalar product happens to equal 0, that just means that two vectors, all three vectors essentially fall on the same plane. I shouldn't say two or more vectors, all vectors are on the same plane. They're coplanar, okay? Which means there's no height to the box. If there's no height to the box because this vector isn't actually here, but it's in the same plane, then you're not going to get a volume at all because there's no height here to take in this box. All right, so that being said, real quick, what we can do is find the volume of the parallelepiped that's used to create the figure using these vectors. So these are the adjacent edges. These are the vectors I could use to create my parallelepiped. I want to do the triple scalar product of those so I can find its volume. Very simply, I'm just going to do U dot V cross W. Why? Because that seems easier. Because it's just easy to write. Actually, no. So this reminds me of something we should talk about. When you're doing the determinant of a 3x3 matrix, again, things you might learn in linear algebra, and if you've had this already, you know this, but these are things that will come up down the road when you get more into matrices and other classes. But when you do a determinant of a 3x3 matrix, if you make the first row the vector that has the most zeros in it, in this case V, it tends to make the computation go a lot quicker. So we're going to do that. So we're going to do V dot U cross W. Order doesn't matter. Remember, order does not matter. But we'll talk about how that's going to affect our answer because we're trying to find a volume. So we'll talk a little bit about that. But anyway, here we go. So that means V is going to go here. U is going to go here, second row. And W here. All right. So that's the determinant we're going to find. Basically do it just like you did cross product, only instead of I, J, and K, you have 0, 2, and -2. So we do the I one, in this case the 0, 1 would give us this 2x2 matrix. So this times this, that'll be negative 5 minus 1. And that multiplies by I, in this case multiplies by 0, minus, the next one would be the j, so we'll call that the 2 component, and it's this 2 by 2 here. And so we would get 3 minus 3, and that would be multiplied by j, but in this case j is taken the place by 2. And then plus the last one, which would be my k, so here, so 3 minus negative 15 times my k is being negative 2. And that's where the dot product comes into play. This is the first component of the cross product. This is the first component of the vector you're dotting with. This is the second component of the cross product. This is the second component of the vector you're dotting with, etc. And that's exactly what you would do when you do dot product, right? You do first components, second components, third components multiplied together, and then add it all up. So you see, by making this vector v be in the first row, you're basically replacing the ijk with those components, and therefore doing the dot product simultaneously. Anyway, what you end up with here is 0. No matter what this is, since it was multiplied by 0, that's why we make that row have as many zeros as possible. That's going to zero out. This just so happens to be 0. So remember, I subtracted, but it's 0 anyway. And then this one would be, 18 times negative 2, so negative 32. So that's my triple scalar product. My triple scalar product is negative 32. However, we were trying to find the volume of this parallelepiped, and that cannot be negative. So the volume should actually be equal to the absolute value of this triple scalar product. In this case, 32 cubic units. I don't know what the units are, so let's just say units cubed. Okay? But nonetheless, absolute value. Now, why did we get a negative? Well, we got a negative because we mixed around the order. And when you change the order in a determinant by juggling up which row goes where, it'll change the sign of your answer depending on how many different rows you move around. Again, something you would learn when you took linear algebra and learn more about matrices. So, that being said, there's our triple scalar product, but if you want it to represent a volume, make sure you always do the absolute value.